Okay, so uh, where is my pen? So far, we have covered, if you remember, statistical notions that were needed in turbulence analysis. And we started with averaging process, the difference between ensemble averaging, time averaging, the stationary process, what is ergodic process, and then autocorrelation and its physical importance, how we calculate autocorrelation functions, and then the probability. And one thing we didn't talk about is how to generate PDF or probability density function for a given signal. I just told you that PDF is the derivative of CDF. And then we talked about the higher order moments, if you remember, in the previous week. So the final thing is to generate the PDF signal, the PDF from a given data. For example, if some data is given to you like this, and the PDF is being asked. Then after this, we will start applying a statistical averaging process to our fundamental equations of motion. So let's see what is histogram. How do you actually calculate the probability density function, and how do you determine which function? I mean, is it Gaussian? Is it Weibull distribution? Is it Rayleigh or something else? How do you determine the function that best represents the probability of the variation of any signal that is given to you? The first thing that we have to do is to plot the histogram of this signal that is given to you. How do we generate it? As an example, I have a list of data in here, and this data is given like this. This is the time, and this is the velocity, for example. So at time equal to 1, velocity is equal to 3.67, and it goes like this. So it's a part of the data that I have. And these values are recorded, for example, by your measurement instrument. And just consider that we have 100 data points. What you do is you start to prepare a plot. And in this plot, you put the values of uh, velocity in determined increments in x-axis. Okay, so uh, this is your x-axis, this is your x-axis, this is your y-axis. Okay, I said you put increment of the velocities in here. So what does it mean? Your y-axis is actually your data count. So let's say between 0 and 1, let's say between 0 and 1 meters per second, how many data do I have? So I count the number of data points that are within this range of 0 and 1 meters per second. And I keep doing this between 1 and 2 and 2 and 3 and so on. Generally, most of the data in terms of numbers should fall around the mean value of these 100, let's say, velocities. And in this case, in this special case that I have, the mean value of the velocities is equal to 4.82 meters per second, for example. And generating such a plot, meaning that if you count the data points with respect to ranges of you count the data points with respect to ranges of is called histogram. So this is a histogram. So in here, my resolution is 1 meter per second. because I am dividing this into ranges of 1 meter per second, right? 0 to 1, 1 to 2, 2 to 3, and it goes on like this. So I don't have to do it like that. I can resolve it much better. If I resolve it much better, it means that I resolve it like this. So I divide it in this second histogram. I made the ranges in zero point 0.1 meters per second increments. So now the question is which one of the PDFs represents these variations best? There are different ways to fit those functions to the histogram. So you remember that I represented you the, for example, Gaussian distribution, right? And I said that this Gaussian distribution is best fitted for your grades for any course that you want. So most of the data will be around, let's say, minus and plus 1 standard deviation. And you remember this. So meaning fitting, meaning put this function on this data. So apparently on this data, you cannot see any Gaussian distribution, but um, uh, there are different ways to feed those functions to the histogram. Let's say if if the Gaussian if the Gaussian best fits the variations, so the first step is to generate the histogram, and the second step, uh, given the histogram, you find the appropriate PDF that best represents this variation. Once we find which function represents in our subsequent calculations, I can then use this analytical or continuous function. So then I don't need to use the discrete values. I just use the analytical formula for the Gaussian distribution, for example. Uh, why? Because you know that I generate PDF, right? You remember that when I generate PDF, then I have to integrate the PDF to find the probability, because this area underneath of the PDF gives the probability. And I cannot take the integral of discrete function. Actually, I can take the integral of discrete function right now using numerical methods, which you probably know. But if you have an analytical function, it's or a continuous function, it's best. It's the most efficient way to take the integral. So I can find the probability of velocities being in the certain range of velocities. For example, I want to find the probability of velocities being in this range. So I will take the integral from this point to this point. That's it. So this is actually the histogram. So histogram again, I told you you have to plot the you have to count your data, and you have to measure how many data points you have in specified ranges. Um, there's a good practice if you use Excel, and you can plot the histogram using Excel very easily. So we have covered a short review of statistical definitions and notions that are frequently used in data analysis and, of course, um related to turbulence. Now, what we are going to do next is actually what Reynolds did in his paper. And Reynolds was important for two things, as you know. First, for the experiments we discussed, and also Osman mentioned, to understand the criteria where the flow changes from laminar to turbulent state, and the definition of Reynolds number. And the other thing is when one applies these statistical averaging techniques to the governing equations of motion. That's the other contribution he did in fluid mechanics. So basically, today, similar to the fact that we call uh, the non-dimensional collection of parameters as Reynolds number, this analysis to obtain the average equation set, we call them Reynolds decomposition of variables. And this is basically a statistical averaging process applied to equation sets. So Reynolds decomposition, all instantaneous parameters are composed of average part and fluctuation part. So you see, for example, you have your velocity in here and your velocity is changing with time. So you are recording your velocity and it is behaving like this. So Reynolds, what he suggested was that um, if you have your instantaneous velocity, you can decompose it into mean velocity and fluctuation part. So this is the notation that we use. Ui is the instantaneous velocity. The mean or average velocity is ui bar plus ui prime for the fluctuation. So in the statistics, we call it deviation, and in fluid mechanics, we call it as a fluctuation. The same happens for pressure, for vorticity, for temperature, and for density. So all variables, all instantaneous parameters are can be composed of an average part and a fluctuating part. If the process is stationary ergodic, so stationary ergodic is the actually name in the statistics, but in fluid mechanics we know that the stationary ergodic process is the, the steady state process. If there is an steady state process, then the average is not a function of time. But if it is an unsteady flow, so in here, as you can see, the average U bar is not a function of time. U bar is something constant. Okay, but imagine this variation. In this variation, like what happens inside the rotor or a stator flow field in a compressor of a gas turbine engine, or the vortex shedding behind the cylinder. Uh, the mean value then also changes with time. So you see that your U bar is a sinusoidal variation. Okay. In a simple steady state, that is, we call this a stationary ergodic case, which is this case, your U prime value is not changing with time. This is generally what we know as Reynolds decomposition of flow variables. So this is decomposition. So where do we use this decomposition? The averaging process, first of all, has some properties. So you have to keep in mind these uh, properties of the averaging process. First of all, the average of the average is the average. That goes nice, right? Average of the average is the average. So ui bar is equal to ui bar. This is one property. The second one, the average of fluctuation is zero. Okay, it means that you can mathematically show this that the average uh, of the fluctuation is zero. How do you show it mathematically? You know that Reynolds decomposition says that ui is ui bar plus ui prime. So take the average of all of these. So this will be ui bar. Average of the average is average. So this is when these two cancel out. So the average of fluctuations will be zero. And we will have some parameters during our manipulation of equations involving the average value times the fluctuation, like this. This averaging can be distributed to this and that. So it means that uh, ui bar times uj prime average, you can distribute this average into this and this. So it is ui bar times uj prime average. And also you can have this another property that when two averages are multiplied and then get averaged, it is the same as two averages as are multiplied. So by keeping these stuff into your mind, just keep this in somewhere. We're gonna play with continuity equation. So the first equation, as we have, is the continuity equation or mass conservation for simple incompressible flow. So we have seen this for the incompressible flow. The conservation of mass is dui over dxi is equal to 0. So you have repeating indices I. It means that it has to be summed over I. So I is equal to 1, 2, and 3. So it means that it is du1 dx1 plus du2 dx2 plus du3 dx3 is equal to 0. And this is true for what? This is true for your instantaneous velocity. This is not true for ui bar, and this is not true for ui prime. So the question is, when I apply Reynolds decomposition to this equation, what will happen? So the first step is to apply the decomposition. So it means that your ui is the summation of mean value and the fluctuating value. And then you will do averaging of on this decomposed equation. So when I do this averaging using the properties that I have mentioned here, this would become like this. So you have average of this thing, which is equal to average of derivative plus again average of derivative equal to 0. So average of derivative is equal to derivative of average plus again derivative of average. So in the second, this means that the original equation that you had here for instantaneous flow is valid for the mean flow as well. If you solve this equation, and the momentum equation written for the mean values, you would get the mean velocity distribution. Okay, this velocity distribution, not the instantaneous velocity distribution.
You are currently the only person in this conference.
So okay, seems that you already left for your meeting. No problem. I will continue, and you can follow up then. Let's say I had solved this latter equation in here with the mean momentum equation, and then I will get the mean velocity distribution, let's say around a wing or an airfoil or somewhere else. Not the instantaneous velocity distribution. I am again saying it. Physically, the last equation, this equation that you see, tells you this. It tells you that the mass conservation should hold both for instantaneous and mean flow properties. The methodology is the same for all the flow equations. So for momentum equation, for energy equation, and etc., you can use the same methodology. I mean the decomposition and then averaging. So next step is to do the same thing for the momentum equation. I will stop the video right now and I will take a break and then come back and uh, continue. Okay, we can continue then. So I will apply it to momentum equation. The original momentum conservation equation for the instantaneous velocity for incompressible flow is dui dt plus ddxj of uiuj equals to minus 1 over root dp over dxi plus nu times del squared u I, and which we talked about before, and we said that it represents three conservation equations for three components. So we have three components of velocity, u1, u2, u3. So in other words, if you write it for all three velocity components, you will have these three equations in here. So if you see in here, why is it representing three equations? Because in this part, j is repeating index, okay? And it has to be summed over j as well. So you see that inside the second term, at each one, j is being summed up. So it is actually summation of three again terms. So the first step was to apply the decomposition, Reynolds decomposition in the first step. So what do I mean? I mean that instead of each ui in here, you put mean plus fluctuation values. So you have ui times uj in here. So this is multiplication of this. And then you have the pressure. So pressure is again the summation of mean value and fluctuation value, and at the end you have del squared of ui, which we put it in here. So as the flow is incompressible, we do not decompose density. As you saw, there is no density in this actually equation because it is incompressible flow. But for velocity and pressure, we applied the Reynolds decomposition. So when you do the multiplication of these terms, you will end up with the last equation that you see in here. So it's pretty straight until here so far. And step two, we said that you need to do the averaging. So for the averaging, you have to average all these terms term by term. So average of this plus average of this plus average of this plus average of this. So if you go back, you see that average of the uh, derivative, average of this derivative is actually equal to derivative of the average. So it will be d dt of ui bar bar plus ui prime bar, and this will be 0, so it will give you actually this term, for example, or this term in here. And then you have ddxj. If I go back, I have to average all of these, so this average will go on top of this, top of this, top of this, and top of this. So from these ones, I know that looking at this one, this this would be the ui bar, uj bar, and again using this one, u average is it's 0, and then this one is 0, and what about this one? This won't be 0, and as you see it in here, um, as I wrote it in here, this won't be zero because it is the instantaneous fluctuation correlation. And then the right hand side can be written like this. And what we generally do is we go one more step and we write the equation equal to dui dt plus. So this won't be zero. So we will use this ui prime times duj dxj plus uj uj bar dui dxj. And this one from continuity is equal to zero. So because the continuity equation we already found it, dui bar dxi is zero. So you can write it like this equation. And then your average momentum equation will be finally equal to this one that you have in here. And if you compare this equation with the original instantaneous equation, if you go back and find the original instantaneous equation, it was like this. So this is the original instantaneous equation. So all the terms are the same, if you see, except this additional term in the mean momentum equation. So the mean momentum equation have all the terms of instantaneous, but this is an additional term that comes inside. So this extra term, it was not there before, so you don't see it in the instantaneous um, equation, and it's a mathematical artifact which is which appeared because of the process of averaging. So because we did this process of averaging, this mathematical thing happens in here. And actually it's a gradient, okay, d dxj, in three directions. So it's the gradient of ui prime uj prime bar. And generally we have three components of velocity, so we can have a composition of nine different forms of these uh, velocity fluctuations, meaning that it is a second order tensor. Because you see that it is ui and uj in here, it would be a second order tensor. And we can see that the gradient ddxj of all of these nine components exists in the mean momentum equation. This means that whatever this term is, whatever the whole term is, the left hand side of the mean momentum equation, you know what is this? The left hand side. This is actually your MA, right? F equal MA. You remember it. Mm. And this means the acceleration is affected, this acceleration is affected by whatever you have on the right hand side as your force. So if there is a pressure difference in your flow field, that will accelerate or decelerate the flow. So this is the pressure, right? If there is some viscous forces or viscous effects because of frictional losses, it will also accelerate or decelerate the flow. And the last one, this term in here, also does the same, but we don't know the physics of this one. So what is the physics of this one is uh, quite a mystery right now for us.